Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Sangita Kumari with us today. Hi, Sangita.
Hi, Frank. How are you?
I am doing very awesome on this, my February 2nd, Thursday. And where are you located, Sangita?
So I live in India, so north of India, and yes, it is summer over here right now.
And it is February 3rd. So we are halfway across the world and we're separated by days at the moment. So very good. And Sangita, what's your position there in Pune?
Yeah, so I'm a PhD student at National Center of Radio Astronomy in India, and I'm in my second year of PhD.
Very cool. Very cool. So I look forward one day to calling you Dr. Kumari. That will be awesome. That'd be very good. Okay. And Sangita, what do you like to do for research?
So yeah, I'm working on supernova remnants, and basically I'm working on pulsars, and yeah, these are very dense supernova remnants of massive stars, which are 8 to 20 solar mass stars. So my research is basically based on these objects.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It's open access, people. You can go get a copy for free. Go grab a copy. Decade-long timing study of the Black Widow millisecond pulsar J1544 plus 4937. And Sangita, take us away.
Yeah, hi everyone. So we have done a decade-long timing of a Black Widow millisecond pulsar 1544 plus 4937. I have done this work under the guidance of my guide, which is Bhaswati Bhattacharya, and the other PhD students, which are Devajyoti and Jayanta Roy. So in this paper, we have actually we have studied a Black Widow millisecond pulsar. So Black Widow millisecond pulsar, they are class of millisecond pulsars. So which are in very compact binary orbit. These are in very compact binary orbit, and I don't know, I'm feeling nervous right now. Sorry, Frank.
It's all good. It's all good.
Yeah, so these are Black Widow millisecond pulsar. These are a special class of millisecond pulsar in which the pulsar is in very compact binary orbit. The orbital period of these pulsars are less than a day.
Okay.
And so these pulsars, so we have carried out a timing of such a millisecond pulsar, which was discovered by GMRT, which is Giant Meter Wave Radio Telescope in India.
Okay.
And the population of these millisecond pulsars, they are steadily increasing with time. But yet the long-term timing of these millisecond pulsars are yet the long-term timing is done for a handful of these millisecond pulsars.
Good. Okay.
So, so pulsar timing, it is a technique by which we can find out the parameters of the pulsar, and so we through observation we find out at what time we are getting the pulses from the pulsar, and we also know like at what time we should get these pulses. So we have observed time of arrival of the pulses from the pulsar, and we also have predicted times, and then we compare the prediction with the observation, and from there we can find out the properties of the pulsar.
Sounds good.
Yeah, so this so we carried out a decade of timing of this pulsar, which gave us very interesting things. So we got for the first time we got to know that this pulsar, it shows orbital period variation. So orbital period variation means that the orbital period of the pulsar is sometimes it is decreasing and sometimes it is increasing.
Okay.
And Yeah, and we also kind of measured how the electron density along the line of sight to the pulsar is varying with time through this timing, and we got to know various parameters of the pulsar.
Oh,
Yeah, this is the model in table 2. This is a model which shows the parameter of the pulsar. So we have very precise estimation of RA and DEC regarding the position of the pulsar. We very precisely have determined the position of the pulsar, which is RA and DEC. And we've also got very very precise values of the proper motion of the pulsar. So proper motion is the motion of the pulsar relative to us, and through this decade of timing we very precisely measured this the proper motion of the pulsar. And then there are other parameters also, like we have got very precise estimation of DM dispersion measure. So dispersion measure is the integrated electron density along the line of sight to the pulsar. And we have then also determined how the DM is varying along the line of sight. So on that we got to know through accurate measurement of the dispersion measure first derivative and second derivative and third derivative. And then we also found that the orbital period for this pulsar is varying, and that we determined from the orbital first, second, third, and fourth and fifth derivatives.
Wow. Okay.
Yeah. So
wow, that's a lot of derivatives. Okay.
Yeah, and can you go to figure 1?
Figure 1. Let's take a look at figure 1. And there we go. Post-timing residuals, looks like. Yes.
Yeah, so now we the metric how good the timing is, the timing residuals are the metric to find out how good the timing is. Like if we have very low timing residual, that means that we very precisely know the pulsar, how the behavior of the pulsar, how it is behaving. And people have now they have gone to nanosecond, up to nanosecond timing residual. That means that they know the pulsar that accurately. So we have got timing residuals in microseconds, and we used kind of two models to model the parameters of the pulsar, two different binary models. And here I'm showing the timing residual using two different models. The first one, the figure which is upward figure, which shows timing residual of 6.9 microsecond. This is with the binary model, which is known as ELL1 model. And you can see that there are still some of the residuals which are not taken care of. There is some kind of systematic trend which can be observed other than the Gaussian noise which is there. And the downward figure shows the timing residual plot using another binary model, which is a BTX binary model.
Yes.
So this is the timing residual plot for this pulsar that we have obtained from 11 years of timing.
Very nice. Very nice. And
so we can go to observation section maybe.
I'm sorry.
Observation section. We can.
Sorry. That was section 2.
Yeah. So the observation for this decade-long timing, all the observations, majority of the observation, they are done with this GMRT, which is Giant Meter Radio Wave Telescope in India, and some part of the observation was done with the GBT, which is in US.
Cool.
And yeah, so here the table 1 shows the summary of the observation. So we have used two different GMRT backends to for the observation. So the first half of the observation, the starting of the observation, which was from 2011 to 2017, it was done using the legacy GMRT system. And then we have observation from GBT telescope, which is in the year 2012. And then at last we had observation with the upgraded GMRT, and
Yeah.
which goes from 2018 to 2022.
Very
So
good.
yeah, upgraded GMRT provides very good sensitivity data because it has very large bandwidth
Yes, significantly larger. Very cool.
compared to legacy and GBT.
Right.
So you can see the fifth column in the table. It shows the minimum flux density, and you can see that the minimum detectable flux density,
Uh-huh.
and you can see that the upgraded GMRT, the minimum flux density is
Two.
lower.
Factor 2 or so. 2.5.
Yeah.
Mm-hmm.
So maybe we can now go on to the results.
Sure. Tables, post signings, residuals, results. Okay.
Yeah. So as I've said that for the very first time, we detected a significant value of the proper motion for this pulsar, and it was not done before. And we have got a significant value, and based on this, we can comment on the formation of millisecond pulsars. So yeah, we got a value of as can be seen that 10.40 milliarc second per year. And based on this value, we calculated the transverse velocity for this pulsar using this relation. And
Yep.
we have got a transverse velocity of 140 kilometer per second.
Ooh, very good. Okay, so it's moving. Very nice.
Yeah, and we also got, as I've said, we have also seen the dispersion measure variation along the line of sight to the pulsar. So dispersion measure is the integrated electron column density, integrated electron density along the line of sight, and it may vary with time. And we have seen that along the line of sight to the pulsar, it is varying with time. And
Okay.
as can be seen from figure 2, maybe we can go to figure 2.
Let's take a look at figure 2. This is a variation of DM. Here we go. Okay.
Yeah, so this shows on the y-axis we have the variation in DM, and on the x-axis it is the time, and you can see that the DM is varying with time. So it is kind of so here the individual points are the DM value that we calculated for individual epochs, and this aqua blue line shows the DM variation as predicted by the model that we have got from this decade of timing for this pulsar.
Okay.
So you can see that the DM is in the starting it is somewhat of increasing, and then it is decreasing with time. And,
0 point. Okay.
yeah.
Mm.
And we have also measured the frequency dependent DM variation for this pulsar. You can go to figure 3 for now.
Yes. Okay, so it does depend. Frequency, DM, different bands. Okay.
So we have used two different the upgraded GMRT bands to observe these frequency dependent DM variation. That means that different frequency waves they are giving so when we are getting receiving the different frequency waves, we are getting different electron densities. The integrated electron density along the line of sight is coming out to be different. So here we have used two different bands. So we have this orange point are the DM values at 400 megahertz, and the blue point shows the DM value at 650 megahertz. And you can see that we are getting different DM values at the different bands. So yeah. So the main reason for this that we found could be that the refraction. So different frequency wave, they get refracted by different amount because of the electron density which is there in the interstellar medium, and therefore we are sampling different electron densities.
Right. Okay. I'm with you.
Yeah, then maybe we can go to figure 3 now. 4.
Figure 4. So we got some period variations, Motion, variation of periastron. Okay.
Yeah, so as I've said that we also observed for the first time the variation of orbital period for this pulsar, and this is kind of seen for other black widow millisecond pulsar population also. So we studied these orbital period variation for this pulsar using epoch of ascending node variation, which is a binary parameter. So this is an orbital parameter of the pulsar, this epoch of ascending node, and so maybe you can go to downward figure. So yeah, so we have seen that we found that the orbital period for this pulsar is varying with time. So as you can see on the y-axis, I have the orbital period, and on the x-axis it is the time, and you can see that the orbital period is sometimes it is decreasing and sometimes it is decreasing, which is in contrast to other binary system where we just see and decay in the orbital period with time.
Right.
And
Interesting.
we also try to figure out what could be the major contributor which is giving rise to this orbital period variation.
Yes.
And
yes.
So yeah, so maybe you can go to section no 4.3. Section 4.3
is the origin of the variability. Okay.
Yeah, so we try to figure out what could be the mechanism which is responsible for giving rise to these orbital period variation that we have observed. So there are a number of contributing factors. The first is like you can go see in equation 2, there are four prominent prominent factors which can give rise to these variations. And the first is the variation in the orbital period due to gravitational wave emission. The second is the variation in orbital period because of the Doppler correction. And the third is the variation in orbital period because of the mass loss from the binary system, and it could include mass loss from the pulsar or from the companion.
Right.
And for now, we have just assumed that there is mass loss from the companion. And the fourth term, which is very important, and it depicts the variation in orbital period due to a variation in gravitational quadrupole moment of the companion. So we actually found out that the contribution from the first three terms are not significant enough, and the last term in this equation 10, this is the main term which is giving rise to the variation in the orbital period. So what is happening is that because since the pulsar and the companion, they're in very compact binary orbit in these systems, so as a result of which uh, these interaction, they give rise to convection in the companion, and this convection along with the rapid rotation, it give rise to the strong magnetic fields, and these magnetic fields then they and then they because of these magnetic fields, there are magnetic torques which results in which allows the companion to sometimes spin very fast, and sometimes it slows down, and because of that its shape changes. Sometimes it gets more oblate and sometimes it gets less oblate. So and because of the change in the shape of this companion, the separation, the orbital period of the pulsar, it decreases, or it increases based on the change in the shape of the companion. So we, for now, we concluded that this could be the major mechanism which is giving rise to the observed variation in the orbital period for this pulsar.
I'm with you. Very good.
And we also and then we also applied some model to verify this further, and from there also we concluded that, like, we calculated the luminosity as given in equation 24, and the observed luminosity is very much close to the predicted luminosity which should be there based on this model. And since the prediction and the observed luminosities, predicted luminosity and observed luminosity are very much same. From here also we concluded that this could be the major mechanism which is giving rise to the orbital period variation for this pulsar.
That's wild.
And
Cool.
at last we also looked for whether this pulsar is good for inclusion in the pulsar timing array. So
Okay.
yeah, and so pulsar timing array is an array of pulsars which using that array people are finding the gravitational waves. People are in a process of detecting gravitational waves.
Nice.
So in general, people they refrain themselves from adding these black widow millisecond pulsars to pulsar timing array. There was this paper from there was this paper Boschning et al. 2016. They argued that these black widow millisecond pulsar should be added in the pulsar timing array, and if their parameters are modeled very precisely. So we in this work we also looked for whether this pulsar that is J1544 plus 14937 whether it can be included in pulsar timing array.
Okay.
And so for inclusion in pulsar timing array, very low timing residuals are important. So we should know how very precisely the behavior of the pulsar. And so for now, we concluded that this particular system is not it will not be good to be added in pulsar timing array, but maybe with later more sensitive observation we can go down to we can more precisely know the behavior of this pulsar. We can reduce the timing residual, and then we can explore the possibility of its inclusion in the pulsar timing array.
Super. Good.
Yeah.
Very cool. Very nice. Beautiful piece of work. Sangita, thank you so much for walking us through your very lovely article on the Black Widow Millisecond Pulsar. Very nice. Let's see. So you touched on it a little bit there toward the end of the article. And so let me ask, where do you think we go over the next 2 to 5 years, or at least over your to your graduate thesis? What are sort of the next steps? Is there additional data in the pipeline? Are we going to be taking additional data? Is there theoretical work that could be done? Just sort of next steps. Where do we go with this? Or are there other Black Widow systems that we have decade-long baselines for? So.
Yeah, so Black Widow millisecond pulsar, these are very interesting systems, and long-term timing has been done for a very few Black Widow millisecond pulsars.
Okay.
So maybe we can carry out this long-term timing study for other Black Widow millisecond pulsar systems, where so studying these systems for a long time, we more get to know about like how they are behaving with time, whether they are showing orbital period, whether all the population of Black Widows are showing the orbital period variation or not. So we are thinking forward to carry this study for other Black Widow millisecond pulsar systems, and we also have more data coming for the system, and we'll extend this timing study.
Nice.
Further.
Very nice. Very nice. I'm predicting a very awesome PhD thesis. It'll be great. All righty. Sangita, thank you so much for walking us through your very lovely article again. Very nice. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.